Look at Deepwater Horizon burning from a U.S. Coast Guard helicopter. The obvious question is, how did a rig with emergency equipment turn into this? The faster answer is also the scarier one. The last barrier did not meet a clean textbook emergency. According to the CSB-linked final report page gathered for this episode, the blowout preventer failed after the drill pipe buckled during emergency well control efforts. That means the device people imagine as the final shut door was facing pipe geometry it could not seal. So the title is not asking why one machine broke at a bad moment. It is asking how an entire safety chain handed the final machine a problem it could not solve. First came signals that had to be read, then choices that kept risk moving, then loss of well control, then at the end, the hardware everyone depended on was no longer working inside the assumptions that made it safe. The frightening part is the order. The final device did not create the whole disaster by itself. It became the place where every earlier error arrived at once. The case is the Macondo blowout and the Deepwater Horizon disaster. Local episode material anchors the human cost plainly. 11 people were killed, 17 were injured, and the event became a wider environmental disaster. Those numbers matter because they keep this from becoming a puzzle about equipment. A rig, a well, people at work, test results, operating decisions, and emergency devices were all coupled together. When the system was healthy, each layer had a job. Read the well correctly, make decisions that preserve room to recover, keep control before the emergency becomes physical. If all else fails, use the blowout preventer as the last line. That sounds like a stack of protection, but a stack can also become a conveyor belt. If one layer passes bad reality to the next layer does not start fresh. It starts late, under pressure, with less room to be wrong. In the good version of the story, each layer buys time for the next one. In the bad version, each layer spends time and hands the bill forward. The myth of the blowout preventer is simple. Everything can go wrong, and then this one device closes the door. It is a comforting idea because it turns a giant system into a switch. Danger comes up from below, the emergency system activates, and the well is sealed. But physical systems rarely grant that kind of clean ending. A final barrier still depends on the condition of the thing it is trying to stop. It depends on where the pipe is, what shape the pipe is in, and whether the emergency it faces still resembles the one it was built to handle. That is why the buckled pipe finding changes the story. The blowout preventer was not sitting outside the chain, untouched by everything before it. It inherited the chain. By the time it mattered most, the question was not just whether a failsafe existed. The question was whether the world around that failsafe still matched the design bet behind it. A door can be strong and still fail if the frame twists. A barrier can be real and still lose if the emergency changes the shape of what must be sealed. To see the failure clearly, split the system into 4 layers. The first layer is interpretation. What do the tests and signals mean? The second layer is decision. What risks do people accept once they believe they understand those signals? The third layer is control. Is the well still behaving in a way people can manage? The fourth layer is emergency sealing. Can the blowout preventer physically stop what is happening? Each layer exists because the next one is worse. If interpretation works, risky decisions can be avoided. If decisions preserve margin, control is easier to hold. If control is maintained, the emergency barrier stays a backup instead of becoming the plan. The danger is that failure in an early layer does not stay early. A misread signal can become a decision can become lost control can become a distorted physical emergency. By then, the final device is not asked to prevent a normal failure, it is asked to rescue every missed chance before it. This is the core pattern in big systems fail stories. The last layer gets blamed because it is visible, but the earlier layers decide what kind of emergency the last layer will face. The first crack in this episode's angle is not flame, it is interpretation. Tests are supposed to turn hidden danger into visible information. They are the system's way of asking, are we actually safe or are we telling ourselves we are safe? But a test only protects you if its meaning survives the room it enters. If the result is ambiguous, inconvenient, or explainable in a way that lets work continue, the signal can stop acting like a stop sign and start acting like background noise. That is the system's lesson in the phrase misread tests. The danger is not that people had no signals at all. The danger is that the signals did not force reality back into the center of the decision. Once a warning can be explained away, the next step can feel less like a gamble. It can feel like ordinary progress. A safety test is supposed to interrupt momentum. If momentum survives untouched, the system has not really learned from the test, it has only learned how to keep moving. In that kind of system, the failure is quiet at first. Nothing looks final yet, but the truth is already losing authority. That is where risk starts moving downstream. A risk decision is not always dramatic. It can look like continuing because the explanation seems good enough. It can look like trusting that the next layer will catch what this layer does not. It can look like treating a fragile margin as if it were still normal margin. The important thing is what each choice does to the future. Good decisions keep recovery options open. Bad decisions spend those options before anyone feels the full cost. In a chain failure, this is how trouble compounds. One layer says the next layer can handle it. The next layer says the last layer can handle it. The problem is that the last layer is made of metal, pressure, geometry, and time. It cannot negotiate with the story people told upstream. It receives the physical state it is given. That is why the middle of the chain matters so much. The disaster is not only in the final impact, it is in all the small transfers of burden that make the final impact harder to stop. Then the story changes from interpretation to control. Lost well control is the moment when the system stops being mostly about readings and explanations and becomes about energy moving the wrong way. The details can get technical fast, but the narrative turn is simple. Before this point, people are trying to understand whether the well is safe enough. After this point, the well is proving that the earlier understanding was not enough. Time compresses. Every delayed correction makes the next correction harder. Every assumption that survived the meeting now has to survive pressure. This is why the Deepwater Horizon story feels so brutal as a systems case. The emergency did not appear in isolation. It arrived carrying the history of how the situation had been read and managed. By the time the blowout preventer became the final bet, the chain had already spent much of the system's room to recover. The later the truth arrives, the less useful it is. At this point, reality is no longer asking to be interpreted, it is forcing a response. Now the thumbnail promise pays off. The failsafe failed. But that sentence is too small unless we attach it to the mechanism. The CSB linked source page describes a final report finding that the Deepwater Horizon blowout preventer failed because of an unrecognized pipe buckling phenomenon during emergency well control efforts on April 20, 2010. Plainly, the pipe was not in the neat condition the emergency seal depended on. The final barrier was trying to close on a problem shaped by the crisis itself. That is why this is more disturbing than a broken button or a sleepy response. The emergency device was part of the same physical system that was losing control. When the pipe buckled, the geometry changed. When the geometry changed, the last line of defense could not deliver the clean seal people imagine when they hear the word failsafe. This is the moment where the whole chain becomes visible. The BOP is no longer an icon on a safety chart. It is a real machine facing a real, distorted pipe in a real emergency. The clean drawing says seal the well. The ugly emergency says seal this, now after the system has already bent out of shape. The machine did not just fail at the end of the story, it revealed how much of the story had already reached it. Think about the counterfactual. If the system had caught the danger while the well was still controllable, the blowout preventer might have remained a backup. If the emergency had arrived in a cleaner physical state, the barrier would have faced a different problem. The tragedy is that the system waited until the ugliest version of the problem reached the last device. When every layer failed together, the result was not an abstract lesson. It was fire, death, injury, and a disaster that spread beyond the rig. The local episode context gives the restrained human line, 11 killed, 17 injured. The broader reference material frames the event as an environmental disaster as well. This is where the chain matters. If you tell the story as one failed device, the lesson becomes too small. Inspect that device better, replace that part, add a stronger final barrier. Those things may matter, but they do not answer the deeper problem. A last barrier is not a substitute for earlier layers. It cannot make ignored signals meaningful again. It cannot give back recovery options that were already spent. It cannot turn a chaotic physical state back into the tidy case the design expected. The cost of a broken chain is that every earlier miss arrives at the same time. That is why the casualty line belongs next to the mechanism. The human cost came from a system that lost the chance to be simple before the final barrier ever tried to close. So, just Deepwater Horizon change about how we judge safety systems? It forces us to stop treating a failsafe like a miracle. A real failsafe has boundaries. It works inside assumptions about timing, condition, geometry, and the state of the system around it. If those assumptions are destroyed before the device is needed, then the device may still exist, still be impressive, and still be unable to save the day. That is the hard systems lesson behind the buckled drill pipe. Misread tests and risk decisions did not stay in the past. They shaped the emergency that the blowout preventer faced. The final barrier was not a magic reset button. It was a component at the end of a chain, and the chain delivered it a worse problem than the clean version people picture. Strong safety design asks an uncomfortable question early. What condition will our backup actually inherit if every earlier layer has already failed badly? When the Coast Guard footage fades, remember the order of failure. Signal, choice, control, barrier. The tragedy was not that safety had no final line. The tragedy was that the final line was asked to rescue a system after reality had already broken the assumptions beneath it. Big systems need emergency hardware, but they also need source truth that survives pressure, decisions that preserve recovery options, and tests against ugly real-world states, not just ideal diagrams. Deepwater Horizon matters because it shows what happens when those layers drift apart. The next time a system promises a final safeguard, the real question is not only how strong it is, ask what kind of damage it will inherit. The failsafe did not fail alone, it failed last.